Welcome to Easy BTech, your guide for BTech and beyond. My name is G. Sampath. I am going to explain the subject VLSI design. Today, we are going to discuss Nmos inverter, Nmos inverter driven by another Nmos inverter, another Nmos inverter, another Nmos inverter, another Nmos inverter, jet pull up by jet pull down ratio, jet pull up by jet pull down ratio. So this is what we are going to derive. It is 4 by 1. We are going to derive this jet pull up, jet pull down ratio 4 by 1. Let us see the diagram. Let us see the diagram. NMOS inverter. So this is NMOS inverter, inverter symbol. This is a symbol of inverter, and internally it is designed by NMOS. Internally it is designed by Nmos. So last class we discussed about inverter. So inverter, the design of a inverter in MOS transistor in digital circuit design, it gives a fully logic 1 or fully logic 0. So if input is degraded, if input is degraded, it gives a fully logic 1 and fully logic 0. So that is a working of inverter, and it can also be restored in NAND gate and NOR gate and some sequential circuits and some memory circuits. And we are seeing different types of inverters are there: NMOS inverter, CMOS inverter, and BICMOS inverter. Last class we discussed BICMOS inverter. So what happens in NMOS and CMOS? We are getting completely output is logic 1, fully 1 and fully 0. But it is not happened in BICMOS. What happens? It is not happened. We are rearranging the circuit. Rearranging the circuit after till it getting the fully 0. It fully 0. Capacitor discharging path. When NMOS is on, capacitor is not discharged. When discharging, it will not completely 0. So till now, till that we redesign the circuit. Now today we are seeing it is NMOS inverter. This is one inverter and this is second inverter. So we are, when these two are connected in cascading connection, so what is this jet pull up and jet pull down ratio? So jet is a impedance. We can take this ratio L by W. We can take this L by W. L is the length of the channel. W is the width of the polysilicon. So with that parameters, the first inverter pull up pull down ratio should be maintained the 4 by 1 and 1 by 1. So in order to drive this second inverter, the jet pull up pull down ratio of the first inverter should be maintained the 4 by 1. Okay, so before going to derive this, let us for equal margins, let us take this for equal margin, for equal margin, for equal margin. So for let us assume this assume, so V in is equal to V out is equal to V inverter. V in is equal to V out is equal to V inverter. So actually when you are applying, let us take V in is equal to 1, output is 0, and output is equal to 1. So it will not equal. But whenever if V in is equal to this V in is equal to 0.5 VDD. If it is 0.5 VDD, then we'll get equal margins. If it will be output of this inverter is 0.5 VDD, 0.5 VDD means VDD is equal to 5 volts. Up to this 2.5 volts, up to this 2.5 volts, then input 1 equal to this inverter and output also equal. So both inverters are equal. So now for this maintain this jet pull up jet pull down ratio, first we can find out the current equations. First we can find out these current equations. IDS of drain to source current we already derived in Nmos enhancement in Nmos transistor saturation region and Nmos enhancement in saturation region and non-saturation region. So we derived this IDS is equal to K into W by L in saturation region VGS minus VT whole square by 2. VGS minus VT whole square by 2. This is a saturation condition. This is a saturation condition. This is a saturation condition. Now IDS of depletion mode transistor K into depletion means it is a pull up transistor. Pull up by length pull up. This is minus VDD whole square by 2. Whole square by 2. Now it is a depletion mode transistor. Depletion mode transistor. Depletion mode where VGS is equal to the previous equation. VGS equal to 0. VGS equal to 0. Now enhancement mode transistor. Enhancement in inverter both transistors are there. In inverter both transistors are there. So K into W enhancement means pull down transistor. W pull down by length pull down. W pull down by length pull down. So in the place of VGS second inverter, so we can take VGS is equal to V inverter minus VT whole square by 2. Whole square by 2. So this is a enhancement mode transistor. Enhancement of second inverter. Enhancement of inverter 2. Inverter 2 where Vin is equal to or VGS is equal to V inverter. VGS equal to V inverter. This one. So in the saturation region, so this will be on and inverter 2 also on. Both depletion and enhancement will be on. For equal margins, we are applying V inverter is 0.5 VDD. Here depletion and enhancement both will be on. Both will be on. Now, so VGS is equal to V inverter. VGS is equal to V inverter. So it is enhancement of inverter 2. This is a depletion mode transistor. VGS equal to 0. Now, equating these two. Let us take this equation 1 and let us take equation 2. So both are on. Both are on transistors. So equation 1 and 2. Equation 1 and equation 1 and equation 2. Equation 2 equal and substituting this V inverter, then we derived this jet pull up jet pull down ratio. So inverting substitution. So equal margins, V in is equal to V out is equal to V inverter equal margins. V in is equal to 0.5 VDD. Assume that we can substitute this V inverter value 0.5 VDD. Then we can derive the first inverter jet pull up pull down ratio directly drive to this second inverter. Now equating this, what happens, K into W pull down by length pull down V inverter minus Vt whole square by 2 is equal to K into W pull up by length pull up minus Vtd whole square by 2. So what happens, the 2 will be cancelled out, and K here constant K will be cancelled out. So we have Z pull up or Z pull down. Z pull down is equal to length pull down by width pull down. So Z is the impedance, which is the parameters of impedance parameters of width of the polysilicon, length of the channel. Z pull up is equal to length pull up by width pull up. Okay, we can write this above equation. I can write this 1 by Z pull down. 1 by Z pull down. If you substitute this length by width, we will get same W pull down by length pull down. Now 1 by Z pull down into V inverter minus Vt whole square is equal to, we can write this 1 by Z pull up, 1 by Z pull up minus Vtd whole square, minus Vtd whole square. Now again further simplification, take this Z pull up left side, Z pull up by Z pull down into V inverter minus Vt whole square is equal to minus Vtd whole square. Now take this Z pull down ratio right side. So what happens here? V inverter minus Vt whole square is equal to minus Vtd whole square by Z pull up by Z pull down. Z pull up by Z pull down. So take the square right side, it should be root. So V inverter minus Vt is equal to the square root of minus Vtd whole square by Z pull up by Z pull down. Right, square and this will be cancelled out. So take this minus Vt right side will be plus. So V inverter is equal to Vt minus Vtd. So divided by, so root will be this root of Z pull up by Z pull down. Z pull up by Z pull down. So in this final equation, we can substitute V inverter value, Vt value, Vtd value. So Vt is equal to 0.2 VDD threshold voltage of Nmos transistor. V inverter for equal margins, it is 0.5 VDD, 0.5 VDD, where VTD is equal to minus 0. Depletion mode transistor threshold voltage minus 0.6 VDD. So you can substitute in this equation. All this you can substitute in this equation. Now we can substitute over here. You can substitute over here. So V inverter is 0.5 VDD. V inverter is 0.5 VDD is equal to Vt is equal to 0.2 VDD. So this is 0.2 VDD. So minus plus 0.6 VDD divided by square root of Z pull up by Z pull down. Z pull up by Z pull down. So VDD common. Take VDD common. VDD will be cancelled out. and 0.2 take this left side, it will become 0.3. 0.3 is equal to 0.6 by square root of Z pull up by Z pull down. If you take this left side square root of Z pull up by Z pull down is equal to 0.6 by 0.3. Now the ratio Z pull up by Z pull down is equal to, so this will be equal to 2, and the root will be taken, it is a whole square. So this is Z pull up by Z pull down is equal to 4 by 1. You see this one, we can say here, for example, let us, it is in transistor representation. It is in transistor representation, so that you can understood this. What is a pull up pull down ratio? So this one is a inverter is designed by, yesterday we discussed, inverter is designed by depletion mode transistor and enhancement mode transistor. Both are in series connection. So depletion is always on transistor because VGS is equal to 0. VGS equal to 0. Then output of this depletion mode transistor as a input to the second inverter. So enhancement mode transistor. This is an enhancement mode transistor. This is the first inverter and second inverter. The second inverter again depletion mode transistor and enhancement mode transistor. You see, so you can say this is a one inverter and second inverter, just a transistor representation. When you are applying V in over here, V in over here, so output of first inverter is inverter output as a input to this second inverter, and this one is the output. This one is output. Now VDD and VSS. So here this is a depletion mode transistor. Depletion mode transistor, we are written the current equation, and enhancement mode also current equation we are written. This is enhancement mode current equations. So Z pull up, this is a Z pull up. You can say Z. Z pull up means is equal to length by width, length of the channel, width of the polysilicon, the impedance from polysilicon from gate to channel, length of the channel and width of the polysilicon. Now here also Z, this is a Z pull down. The ratio is length by width, length by width. Okay, length by width. You can say this length by width, length by width. So Z pull up and Z pull down. So first inverter is directly connected to this second inverter in cascade. The length and width ratio is Z pull up is 4 4 by 1, 4 by 1, and this one is 1 by 1, 4 by 1 and 1 by 1. So 4 is a 5 micrometer length and W is a 5 micrometer width, 1 by 1. So length and width should be 1 micrometer and 1 micrometer. Second inverter driven by this first inverter should maintain Z pull up 4 by 1 and Z pull down 1 by 1. So this is the uh, derivation about this pull up pull down ratio of inverter. Second inverter driven by first inverter 4 by 1. Let us see the another one is NMOS inverter. NMOS inverter, NMOS inverter driven by another inverter, another inverter, another inverter through pass transistors. through pass transistors. If you are using one inverter to another inverter, pass transistors are there. Nmos pass transistors are there. Pass transistors. So what is the jet pull up pull down ratio should maintain of the first inverter? Jet pull up by jet pull down ratio. So that is we are going to derive this is 8 by 1. Now if pass transistors are there in between two inverters, now what is the pull up pull down ratio of a first inverter? So let us see this one. One inverter is here designed by NMOS transistor, and through pass transistors the logic is passing through the pass transistors. That is nothing but NMOS transistors are here. NMOS transistors are here. The second inverter. The second inverter. Now this is a V in we are applying. Let us point A. This is inverter of one inverter, and output this one is B. Pass transistor input is VDD or 5 volts we are applying. So inverter 2 input, this is output. Input is a pass transistor threshold voltage VTP. VTP is the pass transistor of NMOS pass transistor threshold voltage. VTP is the pass transistor threshold voltage. Pass transistor threshold voltage. So input to this one. So input is this pass transistor is VDD and the threshold voltage is VTP. So it is as a input to this second inverter is VDD minus VTP. VDD minus VTP. Output of first inverter goes through this pass transistor. So the logic is through this, and it will be degraded by this threshold voltage. So VDD minus VTP as a input to this second inverter. So we can say this one equivalent circuit representation. Equivalent circuit. It will represent an equivalent circuit. Equivalent circuit. Let us see this in equivalent circuit. Be like this. It's a depletion mode transistor. And enhancement mode transistor. Output. Now here also we can take the second one. Second inverter. Inverters is depletion mode transistor and enhancement mode transistor. Depletion and enhancement mode transistor. So it is represented in equivalent circuit representation. Input is VDD. And the transistor one depletion mode transistor, and current source is I1. Inverter 1. In inverter 1, depletion mode transistor and enhancement mode transistor. So the enhancement is a resistive region. So output 1 is equal to output voltage is equal to the product of current and resistance. Current is a depletion mode transistor. R1 is a resistive region transistor, enhancement mode transistor. I1 is a current source. I1 is a current through this depletion mode transistor. R1 is a resistive region. I1 into R1. Here also input is VDD and transistor T2, second inverter, and current through this depletion mode I2, and R2 is a resistive region. So output is V out 2, V out 2. Now V out 2, V out 2 is equal to V out 2 is equal to I2 into R2. So this is ground potential I2 into R2. I2 is a current through this depletion mode transistor. R2 is a resistive region of enhancement mode transistor inverter 2. So let us take this equal margins. V out is equal to V2, V out 1 equal to V out 2, equating this, and we can find out the I1 and R1. We can find out this I1 and R1 and I2 R2, I2 R2. So from this we can derive the jet pull up, jet pull down ratio 8 by 1. So first we can find out this R1 and I1. So R1 is equal to, before that R1, let us find out the R1 resistive region, resistive region, resistive region of inverter 1, resistive region of inverter 1. So we are going to find out this R1. Let us write the current equation, IDS1. So drain to source current of enhancement mode transistor. So K into W, it is enhancement pull down 1, first inverter, length pull down 1, and input is VGS minus VT, means VGS is equal to VDD minus VT into VDS1. It is a non-saturation. Resistive region means flow of current is low. So resistive region means non-saturated region. We derive this non-saturated region. So VDS1 by VDS1 whole square by 2. We derive this. Now from this, take this VDS1. We are going to find out this resistive region R1. So K into W pull down 1 by length pull down 1. So VDS1 is take common. VDS1 VDD minus VT minus VDS1 by 2. This is IDS1. So we can write this IDS1 by here multiplying. Take this VDS1 by IDS1 by VDS1 is equal to K into W pull down 1 by length pull down 1, and this input is VDD minus VT minus VDS1 by 2, VDS1 by 2. So we can take the output of first inverter in equivalent circuit, I1 and R1. So R1 is equal to, so 1 by, if you take this 1 by, then V by I. So VDS1 by IDS1, it is 1 by K. 1 by K. It is 1 by W by L, means L by W. L by W, I can write this jet pull down 1. Jet pull down 1. We can write 1 by VDD minus VT. 1 by VDD minus VT. So VDS1 is small. VDS1 is small. VDS1 is small. So VDS by 2 is negligible. VDS by 2 is negligible in this. So it is a resistive region. So current through this very less. So voltage is also less. Drain to source voltage is less, and VDS by 2 is negligible. Negligible. So this is a R1. Put in a box. Resistive region of inverter 1, and let us find out this R1. Let us find out this. We already derived R1. Now find out this I1. I1 is a current source of depletion mode transistor. K into W pull up 1 by length pull up 1 depletion mode transistor minus VTD whole square by 2. Now V out 1 is equal to, let us find out V out 1. V out 1 is equal to I1 into R1. I1 into R1. So what is I1 here? So I can write this K into 1 by Z pull up 1 minus VTD whole square by 2 into, so what is the R1? R1 is 1 by K Z pull down 1 by VDD minus VT. 1 by K, it is Z pull down 1 into this 1 by VDD minus VT. VDD minus VT. Now K and this K will be cancelled out. We can write this Z pull down 1 by Z pull up 1 into this. I can write this 1 by VDD minus VT into this minus VTD whole square by 2. This is V out 1. So keep in a box. Keeping this in a box. Similarly, we can find out the V out 2. Similarly, we can find out this V out 2. V out 2 is equal to I2 into R2. So I can write from the V out 1. You can write from the V out 1. So I2 is nothing but K into 1 by Z pull up 2. Into this minus VTD whole square by 2 into 1 by K. This is R2. So Z pull down 2. 1 by, and what is the input? Input of inverter 2 is VDD minus VT. VDD minus VTP. VDD minus VTP minus VT. So VT is a threshold voltage and input is a VDD minus VTP. So here K and this K is cancelled out. So equating this V1, V out 1 is equal to V out 2. Then we can find out the Z pull up 2 by Z pull down 2. The ratio we can find out. So what is the V out 1? V out 1 here, Z pull up 1 by Z pull down 1 by VDD minus VT into minus VTD whole square by 2 is equal to, this is Z pull up 2 by Z pull down 2 into 1 by, so VDD is nothing but VDD minus VTP, VDD minus VTP minus VT into minus VTD whole square by 2 whole square by 2 ma. So this is one of the derivation, important derivation. This VTD will be cancelled out. Now we can write this we can write the equation. It is Z pull down 1 by Z pull up 2. V out 1 is Z pull down 1 by Z pull up 1. Now this is pull down 1 by pull up 1. So this is also pull down 2 by pull up 1, pull up 2, pull down 2 by pull up 2. Now take this left side, we can find out this pull up 2 by Z pull up 2 by Z pull down 2 is equal to take this Z pull up 1 by Z pull down 1. So it is multiplying. If you take this, if dividing, if you take this multiplying, VDD minus VDD minus VT by VDD minus VTP minus VT minus VT. Okay. So let us substitution this VT is equal to 0.2 VDD, 0.2 VDD and VTP is equal to 0.3 VDD. So for equal margins, we are finalizing this and substitution this. Now Z pull up 2 by Z pull down 2 is equal to, so Z pull up 1 by Z pull down 1. So we can substitution over here. We will get this 0.8 by 0.5. So it is a ratio. So Z pull up by Z pull down 1, we already seen this one. So the ratio here it is 2. So 2 into this 4 by 1. 2 into this 4 by 1. This will be equal to 8 by 1 ratio. So the second inverter pull up pull down is driven by second inverter by the first inverter. The ratios of first inverter is 8 by 1. Should maintain the ratio 8 by 1. So Z pull up 2 by Z pull down 2. Z pull up is a depletion mode transistor, pull down 2 is a enhancement mode transistor. Okay, this is very important derivation in the external examinations. So go through the derivation and practice this. Please subscribe the channel, like and share with your friends. Thank you.